Hello everyone, my name is Tyler Yaklovich, and today I'd like to discuss with you a project that I conducted with the help of the Utah Army National Guard Environmental Resource Office and Dr. Kip Solomon at the University of Utah Department of Mines and Earth Sciences. We're going to be looking into quantifying surface water influence on a series of springs in Bluffdale, Utah. So to begin with kind of the macro context of the problem, the Jordan River flows out of the north side of Utah Lake across the Utah Valley, Salt Lake Valley, before discharging into the Great Salt Lake. Along that river's course is a location known as the Jordan Narrows. The Jordan Narrows is an incised river valley that bisects the east and the west Traverse Mountains. It's what flows through the area that us Utahns call the point of the mountain. Now, this study area is within the Jordan Narrows, and to be more specific, it took place in a location called Hidden Valley. Hidden Valley contains two sets of springs, about 400 meters apart from one another. Now, these springs are utilized by the Utah Army National Guard as a source of drinking water for Camp Williams State Military Reservation around a mile to the south. Now, before I got involved with this project, a series of geochemical evaluations and spring delineations had been completed by environmental professionals around the state. Firstly, age dating was conducted on the two sets of springs by Dr. Kip Solomon at the University of Utah. And he discovered that springs A through D have a recharge age or transit time of less than 5 years. The water is modern. However, springs E through F, just 400 meters to the south, have an apparent age of well over 50 years. Now, these results are corroborated by tritium, noble gases, sulfur hexafluoride, and stable isotope analysis. In addition, the stable isotope values for springs A through D show an evaporated signature and attenuated variation compared to precipitation. This suggests that there is some surface water influence on the recharge of the springs. Springs A through D also plot along the same slope as the Jordan River, where springs E through F plot directly on the local meteoric waterline. This would seem to suggest that springs A through D are being influenced by surface water in the Jordan River, and springs E through F are being recharged in an alpine environment far away, directly being fed by precipitation. In addition to those analyses, the chemistry of the water is completely different. Springs A through D have a much higher total dissolved solids, chloride, sodium, sulfate, magnesium, and potassium concentrations than springs E through F. And this is quite perplexing. I mean, these springs are extremely close to one another. You'd expect them to have similar recharge patterns, similar chemistry, but they are extremely, extremely diverse. So the geochemical evaluations that had been conducted on these springs made it clear that there's some surface water influence occurring. And it turns out that there is a diversion of the Jordan River called the East Jordan Irrigation Canal right next to springs A through D. It's about 50 feet up gradient in elevation and just 100 feet or so to the east of the springs. So this seemed to be a pretty likely culprit for recharge to the springs, but how do we quantify that influence? Well, one method of quantifying groundwater influence is known as differential flow gauging, or seepage run, which essentially entails taking one upstream flow measurement at a transect of the stream cross-section and a second downstream flow measurement. Differences in flow between the up and downstream measurements are attributed to groundwater interference. If the flow increases, then we assume the stream is gaining water from the ground. If it decreases, we assume it's losing flow. So with the help of Bert Stolp, the U.S. Geological Survey, we conducted differential flow gauging on the East Jordan Irrigation Canal. And we found that there was actually an increase in flow of about 1.5 CFS from our upstream to downstream sites. This would lead us to conclude that the stream is actually gaining water from the ground. However, it's important to note that our 1.5 CFS differential is smaller than our uncertainty of about 2 CFS, and the springs that we're trying to quantify influence on only have a mean flow of about 0.9 CFS. So while differential flow gauging is an extremely useful method, we concluded that it was essentially inconclusive for this specific site. So we need a bit more precision to constrain our estimate. And this is where the automatic seepage meter designed by Dr. Kip Solomon and colleagues at the University of Utah comes into play. The seepage meter is constructed of a thin-walled tube which is driven into the stream bed. Atop the tube is a control unit which contains two probes to measure the water level in the tube. There is also a valve affixed to the side of it. So the tube is driven into the stream bed, and before a measurement is taken, the valve is set to open. This allows the water level in the tube to equilibrate to the water level in the stream. At this point, the water level or stream stage is measured, the valve shuts, and then the water level inside of the tube begins to change in response to groundwater interference. The water level will rise for a gaining stream, as pictured here, or drop for a losing stream. The control unit measures this change in water level and stores the data, which is then converted to a water level, height, versus time curve as pictured here. If a second order polynomial is fitted to this curve, and then the slope of that curve at time equals 0, that is, the slope of that curve at the very moment the valve closes, it turns out that is actually a direct approximation of specific discharge as used in Darcy's law. This is in units of length per time. So it's the height of water level that is lost per unit time in that specific point. After about the 30 minutes it takes to conduct a measurement, the valve reopens, things re-equilibrate with the stream stage, and then the measurement is repeated. This continues until the meter is either shut off or the battery runs out in the control unit. Now it's important to note that this is an extremely precise method. The probes are actually able to discern water level measurements within a tolerance of about 100 microns, so this is very high precision. So we applied these seepage meters throughout the length of the irrigation canal adjacent to the springs and within the spring's presumed recharge zone. We placed meters along the center line of the canal at 15-meter intervals, and during the course of 4 non-consecutive field outings, we took a total of 255 individual seepage measurements distributed across 21 discrete measurement points. Now each of these measurement points produced a mean seepage flux in centimeters per day. That is for each measurement point. And these are our results. We found that nearly every single measurement point produced a small amount of negative or downward seepage, although there were 2 points which had an appreciable significant amount of upward seepage. Now these locations where upward or gaining seepage is occurring may be due to hyporheic flow, wherein water that is discharged from the canal upstream takes a looping flow path under the stream bed before discharging back into the stream, or it could simply be due to spatial variations in seepage. The uncertainty on these measurements is obtained by calculating the standard error of all flux values recorded at that specific point. So all in all, we found that there was a small amount of negative seepage occurring. Now, taking those individual mean seepage fluxes and finding the arithmetic mean of them, as well as propagating the uncertainty from each of those measurements, can produce a representative seepage flux for the entire length of canal measured. And that representative seepage flux was calculated to be negative 0.9 plus or minus 2.1 centimeters per day. So that means that on average, throughout our study area, the water level in the canal drops by around 1 centimeter per day, meaning the canal is losing 1 centimeter of water height per day. Next, we took this specific discharge, this height per day, and we applied it to the surface area of canal within the spring's recharge zone as identified by previous delineations. So this is essentially multiplying a height by a surface area to come up with a volumetric seepage rate, or a volume that is discharging from the canal. And this came out to about 181 plus or minus 444 cubic meters per day, or 0.07 plus or minus 0.18 CFS. Now our uncertainty is still higher than the magnitude of seepage occurring. However, it's important to note that our error has been reduced by about 10 times. Differential flow gauging produced an error of around 2 CFS versus our 0.18. Now, if we take this seepage rate and we apply it to 1 year, we conclude that annually about 3.3 times 10 to the 4th cubic meters seep from the canal into springs A through D. Now, to figure out what proportion of the spring flow that may account for, we take the total flow through those springs in 2021, which was 6.4 times 10 to the 5th cubic meters, and divide that seepage by it. This leads us to an estimate that around 5% of spring flow may be attributed to seepage losses from the irrigation canal. However, there are some caveats to this estimate. First of all, we saw higher than typical uncertainty from the seepage meters during this project. We concluded that perhaps vibrations from the gravel pit nearby or I-15 may have increased our uncertainty in the meters, but it was pretty consistent that we saw a higher amount of noise in the data than is typical from the meters. We also made some pretty large assumptions regarding the recharge zones of the springs and flow paths that may be occurring. For example, we are assuming that all discharge occurring within the spring's delineated recharge zone is making it to springs A through D and discharging, when in reality, some of it is likely discharging into the Jordan River or other springs and seeps in the area. We also saw high spatial variability in seepage. For example, during Run 3, our third field outing, we had very low uncertainty and relatively high seepage occurring. So it's possible that a larger spatial scope for this study would have uncovered areas that had much higher seepage, or perhaps areas that had more gaining seepage. And so larger spatial scope may have captured that variability a little bit better. In the future, we'd like to install shallow monitoring wells so that we can contour the water table and kind of constrain those flow paths a little bit more. So due to these kind of assumptions and limitations, we consider our 5% estimate to be essentially the maximum possible contribution the canal could be providing to the springs. So let's run through this whole thing one more time. We conducted 255 automatic seepage measurements along our 400-meter transect of the East Jordan Irrigation Canal, which was directly adjacent to our springs we're trying to quantify influence on. This led us to a representative seepage flux for the study area of just under 1 centimeter per day. Applying this height per day seepage flux to the area of canal within the spring's delineated recharge zone results in a volumetric seepage rate of about 0.07 plus or minus 0.18 CFS. And comparing that output, or that input to the springs, to the annual flow through the springs, results in an estimate of around 5% of spring flow being attributed to seepage losses from the canal. So due to these findings, we conclude that the irrigation canal is not a primary source of recharge to Hidden Valley Springs or a primary contamination vector for it. In the future, we think that more seepage measurements, the installation of shallow monitoring wells, and continued geochemical evaluations will help constrain these estimates. Now, these results are extremely interesting to me and extremely disparate from what I expected. I think if you took anyone out to this location and you showed them the spring and you asked them, where's the water coming from, they would look uphill, see the irrigation canal, and immediately assume that that's where the water's coming from, or at least a large percent of the water. There are a whole series of canals in Utah Valley that it's pretty conclusive are losing water to the ground. It's even being proposed as a potential method of aquifer recharge, leaving water in these canals. However, it appears that the East Jordan Irrigation Canal, at least in the area we studied, is actually rather well sealed from seepage, which is counter to what we expected and quite interesting from an engineering standpoint. And finally, I would be remiss if I didn't thank the Utah Army National Guard for allowing me to conduct the project, Dr. Kip Solomon for inspiring the project, providing technical support, and providing the seepage meters, as well as Will Mace, Bert Stolp, and Alex Engstrom for helping me with fieldwork during a very hot summer, in addition to all of the great environmental professionals throughout the state who conducted work on the project before I arrived or did lab analysis for us. And that's my project. Thank you.